So what I did this summer, I've been investigating zero-lag synchronization in a 3-node optoelectronic network. So what does that mean? Can I get a 3-node network to synchronize despite the fact that there are time delays involved? So this was inspired by work by Ingo Fischer, where he used 3 lasers. And we had 2 lasers connected through an intermediate relay laser. And he managed to get the cavities of these 2 lasers to synchronize. So one motivation for studying this is because this is reminiscent to a biological process in your brain where 2 unconnected neurons can synchronize through an third intermediate neuron. So our optoelectronic network. An optoelectronic oscillator is basically a system with a laser that modulates itself with time delays. And that gives chaotic time-delayed dynamics. And so we have a 4-node system. It has self-feedback delays and coupling delays. And we can dynamically remove and add or change the properties of these connections. So first what I needed to do was to see, is this synchrony in a 3-node network possible? So it turned out, yes, we can get this. We can get nodes 1 and 3 to synchronize. And we were able to do that at high values of coupling. In this synchronization, node 2 is completely out of phase with 1 and 3. So this is true synchronization between 1 and 3 relayed through 2. So then I investigated how this depended on time delay changes. So what I did is I changed the time delays for our node 1. And I first changed the feedback delay. And so it turned out that changing the feedback delay keeps synchrony constant, of relatively good quality, and it doesn't induce any lag. However, here in our coupling delay diagram, we can see that changing the coupling delay induces a lag between nodes 1 and 3. So you see here that when we decrease our coupling delay for 1 starts to lead and has dynamics ahead of 3, whereas when we increase this delay, 1 lags and has dynamics behind of 3. So it was quite suspicious that over here, even when changing our feedback delay, we still had good synchrony. We didn't expect that. So it turns out that that's because the synchrony in our system was coming more from driving from the central node rather than relaying through the central node. So we were coupling at a high value of coupling, 0.85. So that means that 85% of our signal in our outer nodes is coming from the central node, whereas only 15% of their signal is coming from their own feedback. So it turns out that our outer nodes were synchronized into our inner node more because their own feedback was being drowned out rather than them talking to each other in some sort of way. So then I looked at a 4-node chain network for comparison. And I couldn't find synchrony here. Here we see different values of coupling and a synchronization error in our network between all possible combinations of nodes. And it goes to 0 nowhere. So this network couldn't synchronize. And that's because of the absence of a central driving node. Then I looked at a 4-node star network. And this one does have a central driving node. So it turned out we could get synchronization here. Because as you can see, the errors between the outer nodes went to 0 for high coupling. So what can we infer from this? So one thing that we can infer is that symmetries in our network can cause similar dynamics in nodes and similar statistics in nodes. So let's look at these 3 pictures. We see symmetries here. Nodes 1 and 4 are in a way related to each other because they're connected by this mirror symmetry. Same holds for our 3-node network. And our star network, we can rotate our network around and swap around nodes 1, 3, and 4. So we would expect nodes 1, 3, and 4, because they're symmetric in some way, to have similar dynamics and similar statistics. So perhaps by looking at symmetries in our statistics, we can find symmetries in our network. And so we can do this, because if we look at these diagrams from earlier, and we look at this network over here, you would expect similar dynamics between nodes 1 and 3, 1 and 4, and 4 and 3, because they are related in the same way. And as you can see, that their synchronization errors all match up equally here and move on the same line. And 1 and 2, 2 and 3, and 2 and 4 also move in the same way. We see similar effects in our 4-node network. So to conclude, I demonstrated zero-lag synchrony in a 3-node network. This synchrony was due to driving. Zero-lag synchrony was also replicated in a star network, but it was absent in a chain network. And by looking at the statistics of networks, we can infer something about their symmetries. Thank you.